Well, this is, I call this my glam rock. I collected this back in 1979, and I've been carrying it around ever since. It has pride of place in our house, which means the downstairs toilet. And it's here. It's a big piece. It needs to be big to show the features of the rock. And you can see from the pictures, and this is just that piece of rock photographed three different ways, or two different ways. And it's a Garnet Amphibolite. It's probably unique in the world. And as far as I know, there is nothing that compares with this particular Garnet Amphibolite by virtue of the size of the crystals of garnet. They're commonly fist size. They do go up to 1 meter in size in the area. Where did I collect it from? I collected it from Gore Mountain in New York State, just about halfway between New York and Montreal, right in the middle of the Adirondacks, just east of Lake Ontario. So it's sitting there right up in the Adirondacks. It's actually located at a height of about 2,600 feet. And it has been mined since the 1870s, 1878. And it's reputedly, of course, in America, they hold the world record for everything. They actually said it was the place where sandpaper was discovered or developed, but of course that's not true. But nevertheless, it has been operating since 1878. The pit has now moved to a slightly different geographical location, but it is still, I noticed this week, under the operational management of Chuck Barton, who was a member of the original family. So it was a family-run mine. And when I visited it, I thought it was just a little piece of paradise, because not only was the rock spectacular, but the location was spectacular. And they had their own ski slope. So this was pretty unique. And I thought, well, maybe my ambition should become to become the mine geologist and spend the rest of my days there. Understanding this incredibly complicated rock and improving my skiing. But anyway, this is the hole that has been generated. You can see there's a boulder here in the front with the garnets in it. Geologically, it's located within the Grenville Fold Belt, and the Grenville orogeny is an American name. And it's a Mesoproterozoic, so it's in the order of 1.2 to 0.9 billion years ago, with the formation of Rodinia. Rodinia was the second great continental mass on Earth after Columbia, and rocks of this age where you're forming building continents through accretion of collision of continents exists throughout the major continents of the world. So Africa, Asia, and so on have all got Grenvillian rocks, although they're given different names in those areas. But in North America, or in America, it extends right from down in Mexico right up through into Labrador, you can see there, and of course we have existence of the Grenville metamorphism in northern Scotland and in the Outer Hebrides, and of course you get a lot of garnets there, and any of you who've been there will remember pink sand beaches, garnet being a slightly denser mineral than most, and so is easily separated by hydraulic action. And so that's in detail what you see is in North America. You've got what they call the Grenville Front. Rocks to the northwest of this, up in here, are older. So that's part of the Archean Shield of Canada, where I spent my early days looking for various things, lead, zinc, copper, gold. And here you've got the Grenville Front of, the Grenville rocks. And these particular rocks, the mine is down in here, this portion down here. So here's Lake Ontario, just for location. This is Georgian Bay, which is a branch of Lake Huron. And the other rocks that I brought along this evening, I brought along some stromatolites that I found in Ordovician rocks in this area here. So this white area is what we used to refer to as cover, but it's the Paleozoic. And these Ordovician limestones in which I discovered the stromatolites are just in that area there. There's another rock that I also brought along, which is a large chunk of sphalerite, which is the major zinc ore, and that was from a mine in this zone here called the Balmat Edwards mine, and you can see that the sphalerite again has been heavily recrystallized through metamorphism. If you go down into greater detail, perhaps I should just, so if we look, or dear me, I'll get the buttons right. So if we look down into this area more closely, we're seeing these two maps. Obviously, the lower map is a greater detail of the upper one, and again, it's not that dissimilar from what Mark was talking about with the importance of faulting mineralization and the faulting channeling mineralizing fluids through the crust. And here you've got a large fault running along the base of this gabbro here, gabbro intrusion, and within that you've got the various pits where the gabbro has been metamorphosed into the Garnet Amphibolite. So that's essentially the ore body running along this fault zone. So clearly the fault was probably contributory. For some silly reason in those days, I hadn't got enough money to have a camera. I was a poor kid. And I thought I did have some photographs, but I couldn't find any photographs of my own. And it was before I bought my camera. But here you've got a picture of the wall of the quarry, and you can see the garnets clearly. And what you can also see is the reaction rims, the amphibolite reaction rims around the edge of the garnets, which is a feature of the mine as well. So the actual rock composition is the dark amphibole or hornblende. Hornblende is a sort of a group name, as a lot of these complex minerals are, and in detail they vary a lot, but that's the black mineral. The second one, the plagioclase. The plagioclase is probably the most abundant mineral on Earth, and also thought to be the most abundant mineral on the Moon and possibly Mars as well. So obviously a fundamental part of our corner of the solar system. It's a feldspar and represents a solid solution mineral between albite at one end and the northite at the other. So a sodium calcium solution. And plagioclase again a sort of group name. Garnet is equally a group name. I didn't even bother to try and put up a chemical formula for the composition of garnet. But obviously the ones in Gore Mountain are abnormally large, up to 1 meter in diameter. They have a hardness of 8 to 9 on most fail, which is pretty hard, and an average density of 3.95. The value of this is that the whole purpose of the mine is to extract the garnets, and they want to use the garnets as an abrasive. And it's always been used as abrasive. At the time I went, their main customers were people making cathode ray tubes, and they were using the garnets to polish cathode ray tubes. But now it's used as an abrasive in high pressure water pumps to clean metals and so forth. They separate out the garnet using its density in much the same way as we saw cassiterite being separated in Cornwall. So it's done by effectively mechanical panning on an industrial scale. The other minerals in the rock sample, if you look at it, biotite and orthopyroxene, they're pretty difficult to see with the naked eye. So I don't bother with those. The origin, so the original rock or protolith was a gabbro. It was metamorphosed during Grenville crustal thickening. So as a part of the accretionary process, you've got subduction going on, you've got crustal thickening, and at the continental margin. And they reckon now that the pressures will range from 9 to 10 kilobar and temperatures of 900 degrees centigrade. So basalt, I think, melts at about 1,000 degrees centigrade. So you're dealing with probably plastic rocks. Those pressures, the pressures are always difficult to give a representation. You know, 2 bar in your bicycle tire. When we were involved in, when I was involved in building a gas pipeline, we were pumping the gas up to 140 bar to transport it to the continent, and that's very high. But obviously, 9,000 bar is a lot more than that, and so you can imagine the impact on the geochemistry going on at those temperatures and at that depth.
What sort of depth does that represent?
That's a good question. I don't know.
Okay, sorry.
So they believe, and I have to say there are multiple very complicated papers written on the chemistry of this rock, but they believe that the rock basically was formed in this under these conditions where you've got folding plastic flow and ultimately hydration. So again, the fault comes in as being pretty important in channeling liquids, giving and also allowing a 2-stage cooling within the garnets can be seen chemically through chemical analysis that they've done. They can see a 2-stage cooling. The reaction rims that you see around the garnets, and here you can see these dark fringes. Here you see a single hornblende, which has got a plagioclase reaction rim around it. This light material is the plagioclase, and you can see the reaction rim in the garnet that's sitting on the top of the specimen. Again, they believe that that's a feature of the introduction of fluids during decompression, so causing alteration rims around both the garnets and the hornblendes. And just finally, on the top of the sample, you see this wonderful fractures within the garnet. So sadly, these garnets do not come out as single large crystals. They are fractured, but the miners love that because half the job is already done, because this is a pretty crumbly rock. You hit it with your hammer and it all breaks down into sand of one size or another. But again, you can see the lineation in the fractures here, believed to be brought about by the what they call the myelinitic foliation. So that's the grinding along the fault during the tectonic phase of the formation of the rock and the cooling. So all that's happening within a shear zone. the nice thing about that is that they can crush it easily, and this is their end product, the nice pink sand, which they use as an abrasive material. So there we are. It's interesting that industrial minerals probably constitute much greater wealth than metallic mineral exploration in the world, and this is a rather unusual industrial mineral in an exceptionally unusual rock. So, thanks for listening.
Right.